For part C of this question, we need a new diagram. And part C goes like this. For the same curve and the same line, we now think about a new line. Y equals minus 1/2 x plus k. And this line meets C at 2 points. We want to find a range of k. First of all, let's actually visualize what's going on, because it might not be clear at first. Well, y equals minus 1/2 x plus k is a line that's parallel to our earlier line L. The only thing that this k does is it changes the y-intercept of this line. So if you look here at line L, it only meets our curve at 1 point. This has to happen, by the way, because we get cut off by t equals minus pi over 4. That was the range for our parametric equations. What we need to do then is try and find k so that it's small enough to where our parallel line will bump into this line twice. Let's get a nicer drawing on that. This would be a possible value of k. Because it bumps into our line twice, it needs to hit it at 2 points. If our k was too small, however, this is just small enough. If it was too small, we would either miss our line or we would just touch it at 1 point. So we need k large enough to where we bump into our line at least 2 separate points. So you can imagine this is potentially the largest k, this is the smallest k, and anywhere in between those two, this shaded area, that's our range of values for k which are going to work. What can we do then to find some way of working out k? One idea that usually works for these kind of things is by making the two equations, so the equation of our straight line and the equation of our curve, equal to each other and solving something. If you remember in the last part of our question, we worked out that these parametric equations have a Cartesian equivalent, and that is that y equals 1/2 of x minus 1 squared plus 5. So what we should do then is make this y equals minus 1/2 x plus k and this equation equal to each other and see what information we can get out of it. Let's try it then. So minus 1/2 x plus k equals 1/2 x minus 1 squared plus 5. Expanding out our brackets. Actually, let's do something different first. Let's multiply everything by 2 just to make sure we've got whole numbers and it looks a bit nicer. So minus x plus 2k equals x minus 1 squared plus 10. Can you see I've just times all the coefficients by 2 here. Step 2 then should be expanding this thing out. So we've still got on the left hand side minus x plus 2k, and on the right hand side x minus 1 squared is going to give us x squared minus 2x plus 1 plus another 10 will give us plus 11. Or let's keep going with this. Let's put all the x's on one side and solve it like a quadratic. So this would be on our right hand side. We've got x squared minus 2x, but we need to plus an x. So minus x. And then we've got this plus 11, but we need to move the 2k over here. So we've got plus 11 minus 2k in brackets, and this thing's equal to 0. Now's the time to stop and think for a second. We've made these two equations equal to each other, and it's yielded this information for us. They need to be equal to each other at exactly 2 points though, so that should tell us something about this quadratic equation. Namely, that its discriminant, b squared minus 4ac, must be strictly greater than 0. That ensures that this thing has got two solutions. This is really helpful for us because it should help us track down k. Let's try it. b is minus 1, so we've got minus 1 squared minus 4. A is just 1, so we can forget about it. And c is going to be 11 minus 2k. This is strictly greater than 0. So what we've got here then is 1 minus 4 times 11 is 44. Minus 4 times minus 2k will be plus 8k, strictly greater than 0. If we leave the 8k where it is, we've got 8k is strictly greater than, this would be minus 43, so plus 43 here. And then lastly, k is strictly greater than 43 over 8. That's brilliant so far, because looking at the inequality, k is greater than 43 over 8, that tells us our lower bound for k. If k is any less than 43 over 8, we're going to get the scenario like this one, where we either miss our line, or if it's exactly equal to 43 over 8, we will just touch our line once and have one point of intersection. Let's add this in here then at least. So 43 over 8 must be less than k. Now we're going to work on, well, this will be a less than or equal to, we're going to work on the largest value of k. And we know it's got to be a less than or equal to, because if our line bumps into the curve at exactly this point, that's okay. We're looking for this missing number then. To do that, we need to think about this point, because this point is the highest point that our line can possibly bump into. At the moment we have a value of t equals minus pi over 4 at this point. I wonder if we can find the actual coordinates of it though. We're going to have to use these. X equals 2 tan t plus 1, y equals 2 sec squared t plus 3. So substituting in t equals minus pi over 4, x is going to be 2 tan minus pi over 4 plus 1, and y is going to be 2 sec squared minus pi over 4 plus 3. Okay, here's the time to do a bit more thinking then. Well, tan of minus pi over 4 is going to be sine of minus pi over 4 over cos of minus pi over 4. It's going to be minus 1. Cos is symmetrical about 0 and sine is an odd function. So x is going to be 2 times minus 1 plus 1. 2 times minus 1 plus 1, which will give us minus 1 when we work that out. So the x coordinate over here at this point is minus 1. Let's write that in. We like to find out the y coordinate though, so a bit more thinking is needed here. Sec squared is a bit of a funny function to think about. So let's first of all think about cos. We're much more familiar with cosine. Cosine of minus pi over 4. Because cos is an even function, about x equals 0, that means when we take the minus angle, it's just the same, the value of cos is the same as the positive angle. So cos of minus pi over 4 is the same as cos of pi over 4, which is root 2 over 2. So sec of minus pi over 4 is 1 over cos of minus pi over 4. So it's 2 over root 2. That means sec squared of minus pi over 4 is 2 over root 2 squared. And when we square the top, we get 4, we square the bottom, we get 2. So this gives us 2. Well, now if we know sec squared of minus pi over 4, to work out why we want 2 lots of sec squared plus 3. So 2 lots of 2 is 4 plus 3 is 7. This should give us y equals 7. Okay then, we've got our coordinates at this point. We've got minus 1 and 7. And remember what's really important about that is that y equals minus 1/2 x plus k. At the largest possible value of k, we will hit minus 1, 7 coordinates. Let's substitute those in then to see what information it can give us. So we've got y equals minus 1/2 x plus k. And it goes through this point minus 1, 7. So 7 equals minus 1/2 times minus 1 plus k. We substituted in minus 1, 7. Now we want to solve this to find k. Well, minus 1/2 times minus 1 just gives you 1/2. So what we want to do is take away 1/2 from both sides. And if you do 7 take away 1/2, we'll get 13 over 2. Oh, my chalk's broken. There we go, 13 over 2 equals k. Once again, thinking about that 13 over 2 equals k, that's our largest possible y-intercept to where we hit this. So actually, we have found the value that needs to go in here. It's 13 over 2. As long then as our k is between 43 over 8 and 13 over 2, we're fine. We have 2 solutions to this equality, meeting C at 2 points. And that is part C done.